We're going to do question 19, but first I want to talk a little bit about this equation and where it came from. If you remember back to physics, this is power. P is power, by the way. So power is energy done per amount of time. The faster the energy gets used or transferred, the higher the power. And remember that work is just energy. And it's an energy that comes from putting a force on something and moving it a distance d. So what we've got here is a certain amount of work energy, force times distance. Let's turn that into power. Energy per time, work per time, force times distance over time. Now, what is change in distance per change in time but velocity? So you might remember this equation from physics. It was not one of the most frequently used equations. Oops. That's it, just force times velocity is power. So that was a physics equation. Power equals the force being applied to an object times its velocity. And then later on in Physics 1, you might remember talking about the rotational versions of equations. So the power in rotation, the force would become a torque. That's the rotational version of force, and then the velocity would become radians per second instead of distance per second. So this theta is an angle in radians per time. And this radians per time, your book gives it the variable n. And torque, which was tau in physics, in this book is now just big T. So I think I've now shown why power is T times N. So just to explain this, where does this 3600 come from? That's basically, you can think of that as a conversion factor to put power into the units of horsepower. And then the question is, what are you converting from? So you only use that 6300 number if your torque is in pounds times inches. And your N is always going to be revolutions per minute. But what if your torque is not in pound inches? What if it's in some other units, like the units we are used to seeing in physics, the SI units, newtons times meters? Well, in that situation, then you use a similar equation, torque times revolutions per minute, and then you use a different conversion number down here. So those are the two equations for horsepower that your book gives. So it only considers two possibilities of units, where torque is in Newton meters, or, as we saw back here, if it's in pound inches. So when we look at problem 1219, it gives some values in PSI, other values in inches. So we know we got pounds and inches going on, so we know we can use this equation, Tn over 6300. And the N is given already. We want to know what horsepower can the shaft deliver at 1750 RPM, and conveniently it's already in the right units, rotations per minute. So that's N. That means we just need to figure out the torque. And to find the torque, we use this equation that we have seen before. We just have to solve it for torque instead of maximum stress. shear stress, that is. So if we solve for T, we end up bringing J from the bottom right to the top on the left. We end up taking C from the top right on the bottom left. And maximum shear stress stays on the top. Alright, so now we have to find the identities of some of these variables in the equation that we need to solve for the variable t that we need to put in our equation to solve for the variable p, which is what we ultimately want to get. So we need to go another level away from our ultimate equation here. So I'm going to start another page to solve for j so we can solve for t, so we can use that t to solve for p. If that makes any sense. We've seen how j is pi times the outer diameter squared. Nope, no, not squared. To the fourth. Minus the inner diameter to the fourth. And that's all over 32. Our outer diameter is given as 1.5 inches to the fourth. And our inner diameter is given as 1.1 inches, and we're going to bring that all to the fourth also. So we got J, let's see what else we need to find. We need to get C here. Don't be tempted to just put the diameter. Remember, C is the greatest distance from the center to the outside. So the maximum radius is really what C is. So that would be the diameter divided by 2. And to find the maximum shear stress, well, that's just given to us in the problem. We know our torque is going to be whatever torque we have to use to create this maximum shear stress of 12,000 psi. And that's just given in the problem. So now we can come back and put in all those values for J, C, and T max. So that's what we're dealing with. We spend 10 minutes on a calculator. I'm highly confident that you will come up with this answer. 5,650, and that is pound inches. I think all of the units we were working with were pounds or inches, so if this is a torque, it should be a force, pounds, times the distance, inches. I say I'm highly confident that that is the answer here, but not 100%, because it's not wise to ever be 100% confident. But that isn't the answer to the problem, because we still have to, remember, use that value of t in the equation for power. So we can do that now. We've got power equals 5,600 pound inches times the rotational, or the rotational velocity slash angular velocity that was given. And divided by 6,300. And when we use either one of those two equations for power, the answer is always in the units of horsepower. And that answer here is 157.
Made with Doodlecast Pro.